SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied, and in this module of this course we shall discuss about the steam turbines. You know that we have discussed about the flow nozzles, and we have also briefly discussed about the steam turbines when we have discussed about steam power cycle. So, if we just recall exactly what we have discussed in the context of steam power cycle, then we will be able to see that steam which is produced in the boiler or steam generator, that steam is allowed to flow through turbine. Hence, the working fluid which is flowing through the turbine is steam, hence the name is steam turbine. And while steam is flowing through the turbine, there are several blades which are mounted on the turbine wheel, and in the course of flow through the turbine of steam jets, there is a deflection, and hence that steam jets suffer a loss of momentum, and that loss of momentum is basically gets absorbed by the rotating part of the wheel, and it eventually produces shaft work. So, let us briefly draw the schematic of a steam power cycle. So, this is steam turbine, and which is an important component of this cycle. What we can see that steam while passing through the turbine, the sole objective is to rotate the turbine wheel from where we are getting work output. Now, we have discussed that steam is not directly allowed to go into the turbine. So, let us discuss this aspect today. So, what we can understand that steam which is, say this is 1, this is 2 and this is 3 and this is 4. So, steam at state point 3 is having high pressure, high temperature. So, that high pressure high temperature steam when flows through the turbine, that energy conversion takes place, energy conversion occurs. So, from the flowing stream, thermal energy is now gets converted into the mechanical work or shaft work. So, this energy conversion takes place inside the turbine. So, essentially this turbine, you know that it is a energy conversion device, it is a prime mover, but it is a energy conversion device, and this is used to convert thermal energy of the flowing stream to be converted into mechanical work or shaft work. Now, when we are talking about this mechanical energy conversion, that is conversion of thermal energy into the mechanical energy, this conversion of energy takes place following two stages. So, if we write here that steam turbine is basically a prime mover, right, and where energy conversion occurs. Energy conversion means, as I said, that the flowing stream is having internal energy, thermal energy, that we have learned from basic thermodynamics. So, basically if we consider that is a this is a control volume. So, there is one inlet and there is one outlet. So, inlet stream which is entering into the control volume is having thermal energy. So, for this flow process, the thermal energy that is represented by enthalpy. So, steam which is entering into the turbine is having high enthalpy, and while it is flowing through the turbine, while it is expanding inside the turbine, at the cost of enthalpy drop we are getting some mechanical work, and this conversion takes place here, and for that we need to have certain arrangements. So, this energy conversion occurs following two stages. Let me tell you, that it is not a case that steam which is producing inside the boiler will be taken directly into the turbine. Instead, there will be a few flow nozzles and steam will be taken first into the flow nozzle, and while it is passing through the flow nozzle it will expand, and the sole purpose of providing flow nozzle is to increase the kinetic energy of steam before it leaves or before it strikes the turbine blade. So, before it leaves the nozzle and strike the turbine blades, kinetic energy of the steam jet should be very high, and that steam jet when striking the turbine blade, there will be some deflection, and that is definitely decided by the turbine blades blade angle, and at the cost of that momentum change. So, a loss of momentum will be there, and that momentum will be absorbed by the wheel. So, and it is producing a torque. So, when steam is leaving from the turbine, in the course of this impressing a torque on the turbine rotating part of the turbine, and we are getting shaft work. Now, what I said, so it is the total energy conversion which occurs following two stages. First, high pressure high temperature steam is allowed to flow through the nozzle, wherein it gets a chance to increase the kinetic energy, that jet. So, steam which is coming out from the nozzle in the form of a jet, that steam jet or steam jets is now allowed to flow through the turbine, and when the steam jets flow through the passage between turbine blades, it suffers a loss of momentum, and that momentum is getting absorbed by the rotating part of the wheel, rotating part of the turbine, that is turbine wheel, and we are getting torque and we are getting work output. So, this is how the total energy conversion takes place. So, if I write here briefly that first stream flows through nozzle and high pressure comma high temperature steam acquires high velocity at the exit of the nozzle, right. So, this is basically this is what is occurring, or what is this observation. I mean, this what I can say, that high pressure high temperature steam will be allowed to flow through the nozzle, and at the exit of the nozzle we are getting steam in the form of a jet. So, kinetic energy has increased, and this is what is occurring inside the nozzle. So, this is I am writing nozzle, and then finally, when steam jet with high velocity. So, let me write here nozzle. So, nozzle produces steam jet, and if we write here that that when steam with high velocity enters into the turbine, blades, or I can erase this. So, steam blades mounted on the wheel of the turbine. So, blades are mounted on the wheel of the turbine, right. So, this is very important, blades mounted on the wheel of the turbine deflects the steam jet, right. Consequence is steam jets suffer a loss of momentum, and that momentum gets absorbed by the wheel and producing torque. So, this is how the energy conversion occurs following two different stages. So, this is what is occurring inside the turbine. right. So, these two things are the two stages. So, this plus this, these two stages constitute together the total energy conversion, and we can understand. We can understand that in work or torque is produced or shaft work is produced from the steam which is having high pressure and high temperature at the inlet to the turbine, and that is how this boiler is there, because the sole purpose of this particular device is to generate or produce steam of high pressure and high temperature. Now, you know that what I can understand, that though we could not see the flow nozzles here, but flow nozzles are the integrated part of the turbine. So, steam turbine is essentially an assemblage of flow nozzles and the blades. So, what I can understand, steam turbines, or what we can see from here is turbine, is basically an assemblage of flow nozzles and blades. Steam will be first allowed to flow through the nozzles, that part we have discussed, and then the steam will flow through the passage between the blades, and while steam is flowing we have understood how it is possible to get torque or shaft work, and that is how this device works. Now, what we can understand, that most important part here is if I underline is this one. That steam jets suffer a loss of momentum, and that is what is created by the blades. So, blades which are mounted on the wheel, on a wheel, so blades are responsible for the deflection of steam jets, and depending on the blades of course, and blades used, and of course, the energy transfer process, we can classify steam turbines into two different categories. Let me tell you once again, we have understood till now that if steam jets suffer a loss of momentum, and if that loss of momentum is high, then definitely shaft work or torque that will produce would be high. So, higher the loss of momentum, so if we can extract significant amount of momentum from the flowing stream, and if we can somehow design that momentum would be absorbed by the wheel, we will be getting higher work output. So, steam jet which would be deflected by the blades. So, depending on the number of blades and also the energy transfer process, we can classify. So, blades play an important role in this energy transfer process. So, depending on the number of blades and energy transfer process, we can classify steam turbine into two different parts. So, if I write steam turbine, it is classified into two different types: impulse turbine and reaction turbine. If you have studied hydraulic machines, you also have studied that hydraulic turbine can be classified into impulse turbine and reaction turbine. Similar to that classification, we also can classify steam turbines into these two types. So, if we discuss about the impulse turbine and reaction turbine. So, first let us discuss about the impulse turbine. So, if we discuss about the impulse turbine, so impulse turbine, you can understand from the name itself that it works on the basis basis of impulsive effect. So, impulsive effect, what does it mean? So, basically that this is basically a change in momentum. So, the wheel will rotate solely due to change in momentum of the flowing steam jets. So, impulse turbine, if we try to draw two different, so basically what we have understood, that flow nozzles and blades, these two sets. So, a set of flow nozzle, a set of blade, these two sets constitute together to form a steam turbine. That is what I have said few minutes back. Steam turbine is an assemblage of flow nozzles and blade. So, if we draw the nozzle, and if we draw this is the so I have drawn here. So, this is first row of flow nozzle, there might be multiple nozzles. So, I have drawn only a single nozzle over here. Similarly, this is first row of blades. So, basically I have drawn only two blades only to show the passage which is from between two consecutive blades. So, there will be multiple blades in this row. So, this is called blades. Now, when steam say is entering with a velocity v naught, which is coming out from the steam generator boiler, and when that steam, if we so you can see this is almost the shape is just like a nozzle, flow nozzle, convergent divergent type, that we have discussed. Now, when steam is coming out from the steam generator or boiler at a velocity v naught, and when it is allowed to expand inside the nozzle, it velocity will increase at the cost of the pressure drop, that we know. And so, right. So, if we now use this color, so steam which is striking the turbine blade, say this is V1, and which is coming out from the first row of blades, or sometimes in many books it is written fixed blades, that is nozzle, and moving blades to signify the blades. So, I am writing nozzle and blades with a velocity V2. So, what we can see, that steam entering into the nozzle at a velocity V naught, it is now expanding inside the nozzle, velocity at the exit of the nozzle would be V1, definitely V1 is greater than V naught, and that is why this particular mechanical device is there. Steam which is coming out from the nozzle, or at the exit of the nozzle, steam is in the form of a jet, and that steam jet strikes the turbine blade. So, these are turbine blades. Right, and you can see that after striking, it is because of the presence of blades, there is a deflection of the steam jet, and at which angle jet will be deflected, that depends on the blade designer. And finally, after striking, steam is coming out from the blade at a velocity v 2. If needed, so basically this is called one set, one row of nozzle followed by one row of blades. So, these two rows together constitute one row. So, one row of nozzle constitute which is followed by one row of blades. So, these two rows constitute together to form a stage. So, this is called first stage or single stage. Now, if we right. So, what I said, first row of nozzles, first row of blades, these two rows together constitute to form a stage. There might be multiple stages, and that is why it is called multiple stage turbine. So, for the analysis, single stage is good enough. What I would like to show you now, that impulse turbine, it solely works due to the impulsive effect, that is due to change in momentum of the flowing jet. So, if we try to draw the pressure and velocity. So, you know that if we consider, so this is the V naught, right, and this velocity is now increasing to V 1. So, this is V 1, and finally, while it is flowing through the passage formed between two consecutive blades, there is a drop in velocity, and it is because of this drop in velocity, that is loss of momentum, that momentum would be absorbed by the rotating part. So, basically these blades are only rotating while nozzles are fixed. So, the first row of nozzles, those are not rotating, and that is why in some books this is written fixed blades or FB. So, these are also known as fixed blades, or these are also known as moving blades. So, this particular row is rotating, and velocity would be less. So, this is V 2. Now, we know that at the cost of something, we are increasing the velocity of steam, and what is that particular parameter? At the cost of that parameter, at the cost of a reduction of that parameter, you are increasing the velocity, and that is pressure. So, you know that if we now try to draw, what about pressure? So, this is P naught, which is available with the steam at the inlet of the nozzle, and then while it is steam is flowing through the nozzle, pressure will fall, and at the cost of that reduction in pressure, so this pressure has fall to P 1. Now, when steam is passing through the blades or row of moving blades, then for the impulse turbine there is no pressure drop as steam passes through the blades or moving blades. So, pressure will remain constant. So, this is P 2. So, now we have discussed that the blades or moving blades are designed for this special type of turbine in such a way that there will be no pressure drop of steam while passing through the passage between two blades or passage of consecutive blades, right. So, this is somehow, this particular aspect is different than what is there in a reaction turbine. So, what we can see, only velocity is going to change while steam is passing through the moving blades, and while velocity is decreasing V2. So, V2 is less than V1. So, momentum is getting changed, that momentum is getting absorbed by this wheel, and we are getting shaft work. So, what we can say, what we can tell from this particular analysis is that for the impulse turbine, if we try to write that momentum of steam jets at the inlet to the turbine. So, I am writing here, I am writing here that I am writing that momentum of steam jets at the nozzle inlet, okay, minus so if we try to see that the momentum of steam or change in momentum of steam inside the nozzle is not responsible to produce any torque or work. So, it is basically if I write, this is momentum of steam jets at the blade or blades inlet. Okay. So, at the blades inlet minus momentum of steam jets at the blades exit, at the blades exit. So, momentum of steam jets at the blades exit is equal. So, you can understand definitely these two are not same. Momentum of steam jets at the exit of the blade or blades is less than the momentum of steam jets at the inlet of the blades, and that is how the momentum change or momentum absorbed by the wheel. Which produces shaft work, So, momentum absorbed by the wheel which produces shaft work. So, what we can see that this blades will rotate solely due to change in momentum of the jets. Let me tell you once again, the blades or moving blades which are mounted on the wheel, because this row of fixed blades or nozzles. So, this row of fixed blade or nozzle, this row is stationary, and that is why sometimes it is known as fixed blade. So, that is the blades are fixed as if, because this part is not rotating. So, the row of moving blade or blade, that particular row is rotating solely due to change in momentum of the flowing jet, and that is the impulsive effect. So, and that this momentum of steam jets at the blade inlet and momentum of steam jets at the blades exit, these two momentum are resolved in the direction of wheel rotation. So, I am writing let me if I can mark these two. So, these two quantities, so this I am writing this both momentum both momentum that is at inlet and exit are resolved along the direction of wheel rotation, along the, or I can write yes, I can write something like this, are resolved in the direction of wheel rotation. So, both momentum are resolved only in the direction of wheel rotation, and that is responsible for the shaft work. Okay. We shall discuss while we shall be driving the efficiency, blade efficiency, then we will see that only the momentum which is resolved in the direction of wheel rotation is responsible for the shaft work. Other component is not responsible for the shaft work. Okay. So, what we can understand is that the row of moving blade or fixed blade, this row is rotating solely due to the impulsive effect, that is due to change in momentum. So, if I write now that wheel, that is blades which are mounted on the mechanical part. So, blades are mounted, or I can write like this, blades are mounted on the wheel, blades are mounted on it, wheel rotates solely due to impulsive effects of jet. Impulsive effect of jets, impulsive effect of jets, that is the difference of, that is difference of momentum of the jets deflected by the blades, right, and that is how this special type of turbine is known as impulse turbine. That means, the blades which are mounted on the wheel, and that wheel will be rotating, and that wheel rotates solely due to the impulsive effect, that is the difference of momentum of jets deflected by the blades. So, this is the impulse turbine. Now, if we talk about the another type of turbine, that is reaction turbine, right. So, if we go here, so here the momentum gets absorbed. So, this is get absorbed by the wheel and producing torque. So, the momentum change is solely by the blades or change in momentum of the jets is deflected by the blades only. So, there is no other mechanism to rotate the wheel. So, next if we talk about the reaction turbine. So, next part is reaction turbine. So, if we write the reaction turbine, what we have understood for this particular turbine. So, let me write here impulse turbine rotates, or I can write works solely due to the impulsive effect of the jet. And that means, when there is no pressure drop while steam is passing through the blades or moving blades. Importantly, pressure does not so if we write pressure does not change while steam flowing through blades, right. Okay. So, this is very important. Now, if we discuss about the reaction turbine, you know that again let me draw at least first row of nozzle or moving blade and first row of nozzle or fixed blade and first row of moving blade or blade. So, I am telling there would be multiple blades. So, first row of blades or first row of nozzles. So, if we now draw it, so this is the nozzle or fixed blade, this is blade or moving blade. We are drawing only a few fixed blades, a few moving blades only for the analysis. And if we draw it, then we can draw this. Right. Now, if we try to plot both pressure and velocity change as steam passes through the first row of nozzle and first row of blade. So, say steam which is entering into the nozzle with a velocity v naught, and as usual when steam is passing through the nozzle, it will expand, and at the cost of the pressure drop its velocity will increase, right. And that is how we are writing. So, say the velocity is v 1 and when steam is coming out, that means when steam will enter into the row of moving blade or moving blades, because we have only drawn 2 blades in this first row. So, that steam will get deflected by the moving blade or normal or only blade. So, say this is the velocity and this velocity is v 2. Now, if we try to draw the pressure and velocity quickly, we can see that we all know that velocity, say this is velocity V naught, and that velocity will increase when stream is passing through these fixed blades or nozzle, and when stream is again passing through the passage between these two consecutive blades that we have drawn here, velocity will fall, and say this is velocity V 2. Right. So, that we can see. We have also drawn the same when we have talked about the change in velocity and pressure in the context of impulse turbine. Now, here if you try to plot the change in pressure when stream is passing through both fixed blade and moving blade. So, this is say pressure, this is P naught. You can see that the pressure will fall definitely. So, this is P 1. What we have seen in this particular type of turbine, pressure is remaining constant when stream jet is passing through the passage between two consecutive blades. Blades deflect the steam jet, but the pressure is remaining constant, and that is how this type of turbine is designed, because wheel will rotate only due to the impulsive effect. But in case of this reaction turbine, pressure drops both in fixed blades or nozzle and moving blades. So, still there will be certain drop in pressure, and say this is P 2. So, what we can see that if pressure is remaining constant, what we have seen for the impulse turbine, then perhaps velocity would have been little lesser at the exit of the moving blade. Let me tell you once again. So, what we can see that in this particular type of turbine, pressure drop occurs both in the row of nozzle and as well as blade or moving blade. It is because of this drop in pressure that we can see in the row of moving blades, there will be a little gain in kinetic energy of the steam jet. So, steam will be deflected by the blades, that we can see. Over and above, there is also a little gain in kinetic energy of the jet, and that is due to the drop in pressure, because velocity will increase. If pressure remain constant while steam is passing through the moving blades or blade, in that case velocity would have decreased even more than what we can see here. So, that little increase in velocity due to this drop in pressure when steam is passing through the row of moving blades or blade, steam will acquire little kinetic energy, or jet will get little kinetic energy, or jet will gain little kinetic energy, and that kinetic energy will give rise to a reaction force in the opposite direction, right. So, that reaction force also will help to rotate the wheel. So, what we can understand that that is of course because the steam jet which is leaving from the turbine, which is leaving from the row of moving blades or blades, already has suffered a loss of momentum due to this deflection, but additionally what we can see that since it is designed in such a way that steam jet will be having further drop in pressure when passing through the passage between blades, it is because of this reduction in pressure there will be little gain in kinetic energy, and that little gain in kinetic energy is compared when if pressure is remaining constant when steam is passing through the blades. So, if we can compare that if pressure remain constant when jet is passing through the moving blades or blade, in that case velocity would have been even lesser than what we can see now. So, it is because of this drop in pressure the velocity has increased little. So, as if the jet is gaining kinetic energy. Kinetic gain in kinetic energy will give rise to a reaction force in the opposite direction. So, that will help the wheel to rotate. So, wheel is rotating not only due to the impulsive effect, that is due to the deflection of steam jet by the blades, rather it is the combination of loss of momentum due to deflection of steam jet by the blades plus the reaction force that is there that we can see. So, these two forces together will allow the wheel to rotate. So, that means if we can write that the reaction turbine pressure in reaction turbine pressure drops both in the row of fixed blades or nozzle as well as in the row of blades or moving blades. It is because of this drop in pressure there will be a little gain in kinetic energy of the exiting jet from the row of moving blades, and that kinetic energy will give rise to a reaction force in the opposite direction. So, wheel will rotate due to this impulsive effect as well as due to the reaction force, right. So, for the reaction turbine, let me tell you once again, impulsive effect due to deflection of steam jet by the blades will be there. Above, over and above that impulsive effect, the reaction force that we can see from Newton's third law of motion, that the exiting steam will be having a gain in kinetic energy, and following Newton's third law of motion, that gain in kinetic energy will give rise to a reaction force in the opposite direction. So, this reaction force together with this impulsive effect will be responsible for the wheel rotation, and hence for the reaction turbine one term is defined, that is called degree of reaction. Or that is defined as the enthalpy drop in the moving blades to the total enthalpy drop. So, that means if we write this is delta H, this is moving blades, total enthalpy drop means enthalpy drop both in fixed blades as well as moving blades. So, delta H MB plus delta H fixed blades. So, you can understand that delta H moving blades is only due to the reaction force, right. So, it is because of this reaction force we can define what is the degree of reaction. So, as I said you that the steam jet will gain a little kinetic energy while exiting from the first row of moving blades, because we have considered only one stage in this particular analysis. So, that steam jet which is exiting from the first row of moving blades is having or is gaining kinetic energy, and that will give rise to a reaction force in the opposite direction following Newton's third law of motion, and that reaction force together with the impulsive effect will rotate the wheel. Now, if we need to know what is the extent of reaction that or reaction force that is responsible for the wheel rotation. To understand that, we are defining this term, that is degree of reaction R. So, now you can understand this delta H mb, that is in case of a impulse turbine, purely impulse turbine, this delta H mb is equal to 0. So, I am discussing several cases. So, cases first one. So, when delta H mb equal to 0, then R equal to 0. So, this is a purely impulse turbine, right. And when case 2, that is when delta H fixed blade equal to 0, then R equal to 1, 100% reaction turbine. That is 100% reaction turbine, right. So, 100% reaction turbine is known as Hero's turbine. Example is Hero's turbine. And when case 3, when delta H mb equal to delta H fb, then R equal to half. That means 50% reaction turbine. An example is Parsons turbine. Parsons turbine. So, what you can understand? To understand, we have understood that some degree of reaction force should be there to rotate the wheel in a reaction turbine. Hence, the name is reaction turbine. Now, to know what is the in what extent that reaction force is there in a particular type of reaction turbine, we are defining this particular term, that is degree of reaction, and which is defined as the ratio of enthalpy drop in the moving blades to the total enthalpy drop. And total enthalpy drop is basically enthalpy drop in moving blades plus enthalpy drop in fixed blades. And we have taken 3 different cases, that when there is no enthalpy drop in the moving blades, that is 0, that is a purely impulse turbine. So, turbine will rotate solely due to impulsive effect. When delta H fb equal to 0, that means there is no impulsive effect at all, solely the turbine will rotate due to the reaction force, and that example is Hero's turbine, that is 100% reaction turbine. But a case may be when delta H mb equal to delta H fb, that is these two are equal, then degree of reaction equal to half, and it is known as 50% reaction turbine, and example is Parsons turbine. So, if we try to summarize, we have discussed about the steam turbine, rather operational principle of a steam turbine. From there, we could classify steam turbines into 2 different categories, and we have then discussed about the working principle of both type of steam turbines. And finally, in the context of reaction turbine, we could define one particular term, that is called degree of reaction, which in a sense gives us the extent of reaction force that would be responsible for the rotation of the wheel, and we could see that degree of reactions, we could define the degree of reaction, and we had taken 3 different cases, and we have seen that for a purely impulse turbine, degree of reaction equal to 0. For a purely reaction turbine or 100% reaction turbine, degree of reaction equal to 1, and if the degree of reaction equal to half, then 50% reaction force and 50% impulsive effects, these two will rotate the turbine wheel. So, with this I stop here today.